What happened? Some of you didn't join back or what? Anyway, I'll keep this short, the second class, maybe another 10-15 minutes, okay, or 20 minutes at the most. All right, let me share my screen now. All right, so let's continue. So I was talking about ion implantation, okay, and I was asking you why we need to do this extra effort of charging up an atom by removing the electrons before we bombard them on a surface. Why do we do it? Is it necessary? Okay, that was the question. Now again, I was asking you who throws the atoms? Who picks up the atoms and throws at the surface? Who is there to give that amount of energy to the atoms? Like the same energy that you had given on your ball that you are throwing at the wall, who will give that energy? Okay, so think about it. The best way to accelerate a particle which has charge on it is to use an electric field. It's very simple, right? That means a neutral atom will not be affected by an electric field. Unless the particles are charged, they will not move, right? That means, you understand, I remove some electrons from the atom and it becomes a charged ball, positive charged ball. Now what I do, I have a electrode that has a high negative potential, then automatically there will be a tendency of this positively charged ball to move towards the negatively charged electrode, right? And the same process, the amount of the strength of the electric will decide what speed this will move. Higher the strength of the electric field, more will the velocity of these particle moving down the atom. All right, and that's precisely why we need to charge up an atom, why we need to convert an atom into an ion before we use it to strike a substrate. Because so the substrate is kept at a negative potential, all right, and automatically whatever of these ions that are formed based on the strength of the electric field, which can go up to a few kilo electron volts, you can have a huge force, a huge momentum because of the velocity. Right, mass will remain constant anyway because we are not removing the protons and neutrons. The neutrons basically gives maximum mass, right? So the mass remains the same. We have a charged particle and a lot of momentum, and once they go and strike the surface of a substrate with a very high momentum, they will strike away certain material out from the surface. Like I told you about the metal ball being thrown on a wall, right? So we'll have a lot of these particles coming out because of the impact of these ions, right? And then those can be of various sizes. They can be micro size, they can be nano size, okay? But this is one way of doing it, okay? So that is ion implantation. Okay, so basically you can take out material, you can make holes, okay, you can make cracks on the surface. A lot of things can be done. So you might say, and many experts might question also, is that you're talking about a bottom-up process, but here you are saying that you will use a bulk material to take out the ions, right? Say whatever ion. If I say I want to use gallium ion to make some impact, I'll definitely use a gallium source first, right? To get the gallium atoms and then remove the electrons and make it a gallium ion. And then use the electric field and force the ion onto a surface. That appears to be a top-down process, right? We have a bulk material from where we're taking out the atoms. But then this going and striking, right, generates a lot of free materials, right? And these free materials, now the question is, you think of whether it's a bottom-up process or a top-down process. It appears to be the top-down process, right? Actually, it is both. It's a mixture of top-down and bottom-up processes. Okay, so it is a bottom-up action performed on a bulk material, right? So if the ions come from a bulk source, it has a bottom-up component. Once the ions are formed, ion implantation is bottom-up. All right. But till the formation of the ions, we can call it as a top-down process. We are starting with a bigger chunk and making ions. But after that, whatever follows is a bottom-up process, because we are using those ions or charged atoms to do the work for us and make nanoparticles. All right. The next phase, now the next process is called gas phase condensation. Another term is thermolysis. Right. So basically convert a material into gas and recondense, all right, make it cooler, and then this forms nanoparticles. Okay, so iron nanoparticles can be formed, like I already mentioned before, from ferrocene at a very high temperature, right, by basically converting it in a gaseous form and then recondensation, because uh, to make a nanoparticle we will need at least some hundreds or thousands of atoms together. Okay, it's not one single atom. If it's a single atom, it's an atom, right? So to get that size that we want, which we typically say maybe 5 nanometers, 10 nanometer diameter, we need a few hundreds or a few thousands of atoms together, all right? And we have to do that or create that condition that at least these number of atoms come together and then they stay together. Okay, they have to stay together, unless otherwise it's no point. If they again mix together and form a bulk, then it won't be a nanomaterial, right? So lithium nanoclusters by decomposition of lithium nitride. Okay, so nanoclusters, basically when you're saying is just clustering, many coming together. So it's the same thing we are talking about. It's very, very small crystallites, very, very small particles, maybe say 1 nanometer, 2 nanometer, and they come together and make maybe a 20 nanometer or a 30 nanometer or a 50 nanometer particle. Okay, so that is what we are talking about as nanoclusters, right? So this temperature that we use for the gas phase condensation depends upon the material, what type of nanoparticles, which material you want to use, right? And accordingly, you will have to set the temperature. Solid template synthesis. Okay, that's another process. Template basically means, you know what is a template, right? It's a standard form that is given to you and you basically replicate it. You just put the things in the template and it becomes your nanoparticle, right? So provides a solid template substrate for gas phase deposition of materials on the solid substrate. That means we have the substrate and then we deposit atoms in the gas phase, and the end result is a nanomaterial. Right? So this is considered to be a mixed bottom-up system. Right? Again, like I told you, like the ionic thing, you vaporize, that means it's a mixed system. Okay, it's a top-down, bottom-up mixed system. Final nanomaterial size, shape, and orientation are predetermined by template parameters. Okay. Now, going up to the biological system of making nanoparticles from using the bottom-up technique. So all these syntheses that you guys know more about these than me, I'm sure about that. So protein synthesis, and then nucleic acid synthesis, all those things that you do, all right? So those are also basically ways of making nanoparticles, right? Materials in the nanometric sizes, okay? So you can have all these biological nanomaterials, all right? lipids, all these drug delivery that we talk about using nanomaterials. Okay, they basically are talking about liposomes, okay, small carriers which are biological in nature, and then you put the medicine in the liposome, right? Send it out, and the liposomes, they open up when they go near maybe cancer cells because the pH is very acidic there. They open up in acidic condition, and the medicine is released. Okay, and these particles can have some magnetic property, and we can use magnetic field to take it to where we want to. Okay, all those possibilities are there, and these are mostly, what we call as biological nanomaterials. Okay, so step by step we will discuss in detail as we proceed with the course, right? But of course, you people have to first understand what we are talking about, and that's why, like I told you before, we will lay more stress and we spend some more time initially on understanding the concepts in a very simple form, and then we accelerate after that. Okay, so basically go for an exponential curve of learning rather than a linear curve. All right, so let's spend more time initially on understanding the systems, and I would really request you to study a bit, and we can always discuss in the WhatsApp group. I will share a small ebook with you today, not very detailed, but it's a small ebook. But you people can look for other forms. There are so many books available now. I don't want to prescribe any specific textbook because uh, not a single book will cover everything that we need to discuss. Otherwise, of course, I'll give you a lot of study material. So don't really need a book, but you can if you want to. But then you have to study a bit to understand these systems. And so basically, we will first talk about how we make these nanoparticles, and then we will move over to how to use these nanoparticles that we made. What can be done, right? Or why do we need to go for these nanoprocesses? We will discuss gradually, and therein we will pull in certain examples. And for this particular course this time, because I think all of you are from pharmaceutical sciences, so I'll try to keep all the examples in your domain of interest. Okay. All right, now I'll show you certain images of my own work. All right, just to give you an understanding of how these fabrication processes can happen. All right, so we just talked about using templates also, right? So I'll show you some examples where we talk about bottom-up technique of making nanomaterials and also using biological templates. Now in this one, this is some from one of my work that I started when I was in Thailand at the Asian Institute of Technology. Now I won't go into details of what exactly, because right now we are just talking about synthesis. So I don't want to confuse you with a lot of other things. We will again put this slide later when we talk about applications. But right now, let's have a look. You see those rod-like structures? They are basically rods that are made from a material called zinc oxide. Okay, I personally have done extensive work with zinc oxide, and in fact, if you Google zinc oxide, you'll find a lot of my work there as references. Just a minute. Hello. ধৰিত্ৰী মই ক্লাছ এটা লৈ আছো নতুবা ক্লাছটো কৰি পেলাই কল বেক কৰিছো Okay, so you see here all these rod-like structures. This actually personally it came out from my kitchen. Okay, because when I was working in Thailand, I used to spend a lot of time in the lab, and my friends used to call me up and ask me, what are you cooking now? Because I was exploring all these possibilities of making different nanostructures. All right, so these nanostructures basically started with zinc and oxygen, right? And oxygen, is not easily available in oxygen form, because we did most of these structures are made in water. So oxygen was available as hydroxide, OH, right? In water you have HOH, So from that OH, I used to pull in the oxygen and make this type of structure. This is just one example. I'll show you many. Okay, this is called the nanorod type of nanostructure. Okay, the name is nanorod. Now, what happened here? You see, I was actually, I won't go to details of the application, but I was talking on something unique there, and I needed to generate some energy from these rods. Okay, and I needed some electrodes. Okay, let me see if I have that here. All right, I'll talk about it later, but now I'll talk about this is a typical bottom-up process and it's done chemically. I use a zinc source, all right? It can be any zinc salt like zinc chloride, zinc acetate, zinc nitrate, zinc sulfate, whatever. If you take these and dissolve in water, what will happen? They will dissociate. Now, what does it mean? They will separate out. You all know about salt, right? If you put salt in water, dissolve it, you can rotate it and it dissolves, right? What happens? Where is it gone? Well, it broke up into sodium and chlorine. Sodium chloride is a salt, right? It breaks up into sodium and chlorine, all right? It maintains its unique identity. Sodium remains a sodium. But then if you start evaporating out the water and you get the crystals back again, it will again be sodium chloride. That means chlorine will merge with sodium. Okay, they come together, bond together, and they become sodium chlorides also, right? Same process. That's a salt. Sodium chloride is a salt of sodium in hydrochloric acid, right? Similarly, you can use a salt of zinc in hydrochloric acid, that is zinc chloride. And if I dissolve zinc chloride in water, I'll get zinc separated out from chlorine. All right, it's the same process. So any salt you dissolve in water, you are going to dissociate out. That means separate out the components. So I needed zinc here, so I use some salt of zinc. I can do it anything, zinc acetate, zinc nitrate, zinc chloride, any type of salt. So I get the zinc and I get the oxygen from water and I make these structures like this. All right, that's a simple bottom-up process. Now let me show you another example of the biological template. We just talked about templates being used for making nanostructures, right? Now if you look here at the figure below, you see there are some things I show you. So you see these colorful liquids, they are actually gold nanoparticles, right? That means small particles of gold. And you know, I already told you that everything changes at the nano level. At the nano level, gold is not golden in color. It is only at the bulk or macro level gold is golden, right? So at the nano level, it can have different colors. So you see here, based on the size, the colors are different, but these are all gold, nothing else. It's simple gold, okay? Now, this is a process which we developed when I was working in Thailand. I'll tell you the story sometime later. But you see, what happened was, you know this, right? Everybody knows this. This is a very common fungus that grows on our food when left, open, or maybe there's no electricity. Whatever food in the refrigerator, after some, or one day maybe you'll find this type of fungal growth. All right, the typical fungus called Aspergillus niger. Okay, that's a scientific name. So what happened was, let me tell you this story quickly. What happened was, there was one student from India who was doing his master's at AIT, where I was working at that time, and he was doing some experiments with gold nanoparticles. All right, so to make gold nanoparticles, again, the same thing. I'll use a gold salt to get the gold, and I use some other chemicals. I'll explain why later, but with some other chemicals, all right, and then we make the gold nanoparticles. Now, what this guy did was he made some gold nanoparticles which were quite reddish in nature, something like this, okay, very red and beautiful ones. And what happened, it was just around summer, and he came home to India. I was there. I did not come to home that summer. And he came to India. He left all these gold nanoparticles that he made on the shelf in the lab. And I was working in the lab, and gradually I was observing that, his gold nanoparticles, which were very red in color, gradually started becoming less red. That means lighter and lighter and lighter. And one fine day I saw that it's transparent. There is no more reddish things there. It's totally transparent. And I was at a shock as to what's happening. Where did all this gold go? But I did not touch because it was his sample, and I waited for him to come back. And when he came back, I told him, see, something happened. Your gold, they were supposed to remain red for years and years and years because they are very stable, the particles. But where did all this gold go? It has become transparent. So we opened the cover of the glass container and we saw something floating on the surface, which appeared very black, some fiber-like things. Okay. Anyway, I went back to my work, but this student was very smart. Okay, he had so much of inquisitiveness that he thought that I cannot let this go. Let me find out. So what did was he took out those floating things, the black floating things, put it on a glass slide, and tried to dry it up in the sun. He put it in the sun because he said, let's do a natural process of drying up gradually. He put it in the sun one whole day, and next day, towards the afternoon, he came excited, shouting to me, see, look, look, what happened. And you know that black fiber-like thing that was there, it became totally golden in color. The whole fiber looked golden in color. Okay, and we were so excited as to what happened. So we know now that what happened to the gold. It went to that fiber-like thing, whatever it was. Well, that led to a series of studies. It was a lot of excitement. And my boss got so excited that he actually sent the student to Sweden just to do some studies on these one. And finally, we found out that it was actually the fungus. So whatever chemicals he was using, fungus started growing on them. And what happened as the fungus grew, you see here, I've drawn this picture here, as the fungus grew gradually, it started pulling in the gold nanoparticles to its surface. Right? So what is happening? All this gold is coming and sitting here. And that's why I was seeing the color getting lighter and lighter, because the golds are getting removed from the water and sitting on the fungus. All right. Now, finally, what happened? I'll quickly show you some more pictures and then I'll tell you. You see, these are scanning electron microscope. This is magnified image. This is magnified 70,000 times. And you see all those small balls there on the surface. This is basically the fungus. Okay, we call it the hyphae, the branches of the fungus. And you see all those gold nanoparticles sitting there so nicely. You can clearly see them, right? And this is at a magnification of 70,000 times. Now then, we took an optical image, and you see this image on the left, it is golden in color. That is an optical image, and that's why we couldn't see the color. This is an electron microscope image. We don't see the color. This is in grayscale. But you see, we got these beautiful gold wires using what is called as a biological template, because inside these are only the fungus. The gold is sitting on the surface. So what we did I had that, I'll show you later, okay? But anyway, what I was trying to say that silver is silver at the bulk level, gold is golden at the bulk level, but when you go to nanometric sizes, these are not silver or gold, these are totally different colors. Silver, personally, one of my PhD students is making silver that looks blue, pink, green, yellow, beautiful colors. I'll show you someday. I'll show you pictures, of course, but when you come to the lab, if you come sometime when the university reopens and you come and approach me, I will take you to the lab and I'll show you those beautiful, colorful silver. All right? So very soon you can even think about colorful gold jewelry. Huh? It might be very handy. I say red colored gold jewelry. But anyway, it won't remain red after we agglomerate it, okay? Because it comes to the bulk and automatically it will become golden like these wires here, okay? So the moment all these nanoparticles came together, this picture was taken after annealing it. That means we heated it up gradually. Extensive study we had done this. Actually, my wife did a lot of study on this one. I'll show you some of our results later when you understand this. But she did an extensive study on how to convert these wires made out from fungus to actual conducting wires. Okay, so since we are from electronics and we are working with sensors, and this system that we are developing, I'll tell you a gist of it. We started the work, which is part of my wife's PhD work, is that we want to make a system that will pick up vibrations from the heart, the human heart, to generate energy to give power to electronic devices placed inside the human body. Typical example is the pacemaker. You know, the pacemaker that is put as a backup for the heart. The pacemaker also has a battery in it. My brother has a system put in, it's called as a defibrillator, that also monitors the heart continuously. Now the battery life is about 7 to 8 to 9 years at the most. That means after that time you have to remove it out, replace the battery and put it back again, a whole big operation. But think about it, if the heartbeat itself can generate the energy to keep these systems working, what more can you ask for? We did a lot of studies when I was in Sweden, but somehow we really need to put it on a human to study, which is difficult for us because we are not from the medical background. And I actually convinced a friend of mine who is a cardiac surgeon to help me out. He has agreed, but then, doctors are always so busy. So finally, I thought that I'll make an artificial heart to at least get that pumping. And I'll try to put this system on the artificial heart and try to see how much of energy we can extract. Okay, that is in the pipeline. We're already designing the artificial heart, but you can think about it. So many exciting things can happen, especially in the field of medicine and medical technology in diagnostics, okay, using nanomaterials. Anyway, this is another two examples I gave you. One is a typical bottom-up process, and the other is a template based. Here is a biological template, maybe chemical template also, but templates based nanomaterial synthesis. All right. Now let me, what is the time? All right, let me take another 5 minutes for this class. So you see those beautiful things on the screen, right? Those colorful crystals. These are actually big crystals. Nature has made it. You can see whatever work I personally did till now, because I moved into nanotechnology sometime in 2006. Okay, almost 14 years now that I have been researching in the area of nanotechnology and nanomaterials. So I knew nothing before that because basically I'm a microelectronic engineer. Okay, so I was more into integrated circuit design, fabrication, and all those. And then all of a sudden, what happened once was my hard disk drive, it crashed. Okay, the hard disk in your laptop, right? One of my hard disks crashed, and when I opened it, I found that it is from a company called what was it? Western Digital. I don't know if you heard of Western Digital. Okay, that is American company, but it has a huge fabrication unit in Thailand, where I was working at that time. I was in Bangkok, and they had a huge fabrication unit in an industrial estate called Rayong. That's about I think 400 or 500 kilometers from Bangkok. But anyway, I needed to replace my hard disk, and so I was looking around asking for people because I didn't have much money at that time. I was a poor guy, and I was like, I was supporting my wife's study also, and I was not a rich guy. I was looking for a better option so that I can buy it at a lower cost. Then one of my Thai friends, he told me that there's a exhibition going on in Bangkok, an electronic exhibition. Why don't you go there? You'll get some good discount there. So I went there, and I was bargaining on the same type of hard disk, and I was complaining. I was like irritated. Why did this happen? I mean, this is not very old. It's just 2 or 3 years old, and it crashed. And anyway, the Thai people always has some problems speaking in English, and they were not being able to answer me properly. And then there was this American guy who was standing a little far away, and he was observing me. And then he came and introduced himself. Okay, he's still a very good friend. His name is Pat McPhail, a mechanical engineer from the US. And he told me that I think it's a problem with your filter. Okay, and you might have been using it under very dusty conditions sometimes. Well, it is true. Sometimes I had actually sat out in the open, and they have this wind, a lot of wind there, and might have been possible. So we were discussing about filters because he actually was from a company called Donaldson. And Donaldson is an American company. It's a huge multinational company. They make filters. Okay, and they make filters for everything, right from your cars to the trucks to the aeroplanes to the hard disk drive. All types of filters they make. And we were discussing, he was telling me a little bit about what type of filters are there in a hard disk, and came to know from him that there are two types of filters in a hard disk. Okay, one is called as the Breda filter and one is called as the recirculation filter. Anyway, we were discussing and I said, why do you bother with two filters? Why don't you just put one filter? I just said very casually. And he said, okay, you make it for me. And I also jokingly said, okay, you give me the money. And he said, fine, I'll give you the money if you can do it. And it was time when I was just starting my master's project. Okay, I did my master's at the time. So I was looking for an idea for my master's project. And when he said that, I went back, studied a lot, talked to my supervisor, and said, can we do something? And then he said, maybe nano is the answer. You look into nanotechnology as possible way to solve this. And believe me, it was a lot of study. And finally, when I made the presentation to Donaldson, they were so happy. They immediately funded me for my project 1 year. And after the completion of 1 year, they said you continue because there's still a few more things you can do. So they hired me as a research associate. For 1 year, I was working with fundings from them to develop a single filter for hard disk drive. And that was my first entry into nanotechnology. I didn't know anything about nano at the time. I was just studying. And then I needed to make these nanomaterials. And I also didn't know much about it. And when I was reading all these top-down techniques, and they are so sophisticated. So when I approached my supervisor, I said, sir, how to do this? I mean, I need all these. And he said, I cannot give you. I don't have the money to give you. Find something different. And he gave me a hint. He said, think about Mother Nature. Mother Nature has been making nanoparticles without any sophisticated instrument. Why can't you do it? Okay. And then I started studying natural nanomaterials and found out how nature has been doing, and I tried to follow. Okay. So if you come to the lab, I'll also teach you a few things later as how we can actually follow natural processes and make nanomaterials. So at the time when I was looking and I was studying this, I found this photograph. Okay. This is actually gypsum. I don't know if you know the term. Gypsum is a chemical which is actually calcium sulfate. Okay, and these crystals are actually calcium sulfate crystals, and these are made by nature. Okay, and these crystals are formed about 1000 feet below the earth's surface in a cave. 1000 feet below the surface, temperature was about 80 degrees centigrade inside. Huge amount of humidity, because these photographs that you see are taken by photographers who used to run in, put the light, run out, because they cannot stand the 95% humidity there. It was close to 95%. We cannot survive. So they used to run in, put the light, run out, run in, put more light, run out, and run in, take photograph, run out. That way they were doing it. So after reading this article, I realized that if you have a lot of humidity, you can have a high pressure system and temperature around 80 degrees centigrade, you can make a lot of crystals. And that's precisely what I did. Those zinc oxide rods that I showed you, they were grown at about 90 degrees centigrade in water, right? Same like this process that nature has been doing, all right? So nature is a fantastic thing. They make so many crystals, these are, I don't know if you know them, they are called stalactites and stalagmites. Okay, these are natural crystals in the caves. If you walk into any cave, I don't know if you went to the Mosmai cave in Shillong, sorry, in Cherrapunji. There also you'll see a lot of these stalactites and stalagmites if you enter the cave. Okay, so these are crystals that nature has been making. Okay, so I don't know if you've done this, but have you made these sugar candies when you were kids? I don't think you had time from computer games, right? But at our times, we didn't have any other form of entertainment. Okay, because the first TV I saw was when I was in class 8. Okay, so we used to play around with these. We used to make these type of sugar crystals. Okay, so basically dissolve sugar, make a sugar solution, sugar liquid, that means a solution, a broth, and then put some crystals of sugar on a stick. Some crystal has to be put on the stick, and then we put them in the liquid and slowly rolling it, startly rolling it, and more crystals started forming there. Okay, with the base crystals that I put in, which are called seed crystals, those seeds started becoming bigger and bigger. We used to have these candies. Okay, that was the fun doing it. All right. And when I was working in Sweden, I was playing around with it. This is how I used to look. All right. This is how you work, totally covered up, right? And this is a silicon crystal, right? The same process. It starts with liquid silicon, and you have one small silicon crystal put up here in this tip of the rod, and look at it, that small crystal ended up becoming one huge single crystal. It's a huge one. We call it as a bull. Okay, bull means not bull, it's boule, bull. And it's huge. It can be a few meter long, one single crystal. Okay, all the atoms nicely placed. So this is how crystals form. So what I'll do is, all right, give me another few minutes to show you something very interesting. Okay, like I told you, I was learning a lot from nature, and what happened was the material that I was making at the time, we were trying to use it also after my hard disk drive work. I started my PhD work, and then it was more about environmental nanotechnology. I wanted to use nanomaterials for environmental remediation. In that process, that means sensing environmental pollution as well as removing environmental pollution. And then I wanted to work with solar energy, because if you really want to work in the field, finally you want to clean up rivers, you want to clean up lakes, you need solar energy. You cannot think about using any other form of energy. And these materials that I was developing, they did not absorb solar energy. They used to absorb ultraviolet, so solar has very less ultraviolet in it. Majority part is visible light. And my material that I was making at the time, it was not able to, take in visible light. So we needed to develop a system to make them, visible. So I'll give you an example. Again, I started looking in nature. Okay, I'll stop here after this example, and we'll continue again next week. So nature has been doing a lot of things, and one thing that I came to know is that the optical property of a material, because if you look at the color or the optical absorption, it is an optical property, right? So optical properties vary if we have some defects in a crystal. Now what do you mean by defects? Means the atoms are not in the right places maybe, or some foreign atoms are put in. Okay, that means if I have, suppose I was talking about zinc oxide, so it is zinc and oxygen in the crystal, right? Now if I have some chromium put in, few of them atoms, or maybe aluminium put in, this process is called doping. If I put in some foreign atoms which are not of the original material, then the optical properties change. So look at this now. You see this crystal here, the transparent crystal? It is corundum. It's a natural crystal. Nature has made it. I did not make it. It is corundum, and this is basically aluminium oxide, alumina, right? Now, if we remove certain aluminium from it, and if I say certain means about 1% maybe. If a 1% of the aluminium here is replaced by chromium, you know what we get? We get another crystal which is ruby. Now look at the color change. Totally transparent crystal, just by putting in some foreign atoms, just 1% maybe, or 2% at the most, the color totally changed, the optical property totally changed, it became ruby. All right. So basically ruby's parent is the corundum. Now another example I found is a crystal called beryl, or beryllium aluminium silicate, which is a transparent crystal that nature has made. All right. Same thing. This is also aluminium, right? It's a aluminium silicate. So here also, if you replace some amount of aluminium with chromium, the same here. Here also we replace aluminium with chromium, we get the red ruby. Here we are replacing aluminium with chromium, and you know what we get? We get emerald, which is green in color. Isn't it interesting? You see, simply by putting in some foreign atoms, you totally change their optical properties. Nature has done it very simply. I don't know how nature did it, but that was a hint to me that I can also do it if I try. And I tried it on my material. That is the material I had worked in. I told you, this is just one version of it. There are many other morphologies or shapes I had made. I'll show you sometime. But finally, I will keep a long story short. Finally, I did manage to convert this UV absorbing material into visible light absorbing material. Okay. So we'll talk in details about this, but all these processes I'm talking about are bottom up processes of making nanomaterials. Okay, so what we'll do is we'll stop here today, and do send me the attendance, and I will send you some study materials through the WhatsApp group. Okay, and I will also give you a certain problems to solve, because those numericals, the same numericals on surface area, you should keep on trying. Okay, I did solve a few for you. I did give you an assignment which only one submitted till now. I don't know what happened to the rest. So I will need some effort from you guys also, okay? Otherwise it's not fun, no? There's one guy talking, the rest just listening or sleeping, or I don't know. Or maybe you're not there, only your phone is there. So it's nice, because if you try, you'll find them also very exciting and very interesting. So I'll give you some more problems to solve. And if I give you a problem to solve, I expect you to submit also. I mean, it may not be correct. That's a different issue altogether. I don't expect that all the problems that you will try to solve will be correct at the first go. But we can also work on it. If you give me a solution that is not correct, or maybe half correct, I can discuss and we can redo it, right? And we can make the corrections. So it will need some effort from you. I'll really appreciate it. It won't take much time, maybe even if you weekly you spend 1 hour, that is good enough, I guess, extra about the classes, right? So all right, then I will stop here today, and any questions you can put them in the WhatsApp group, and I'll give you the answers as and when I get the time. Okay, so all right, thank you everyone, and do take care. Right, so you just send me the attendance immediately. Right, thanks everyone. Bye.